Welcome. Today we explore the rigorous mathematical frameworks that define the boundaries of what is knowable. We will bridge the gap between the abstract perfection of logic and the constrained reality of physics, using asymptotic analysis and cost function algebra as our primary tools. To understand computation, we must first strip away the hardware. Alan Turing's machine provides our theoretical baseline. It is defined by an infinite tape, which is an epistemological necessity. It separates the logical steps of a calculation from the physical limitations of memory storage. The Church-Turing Thesis asserts that any effective calculation can be performed by a Turing machine. But the extended thesis goes further, claiming that a Turing machine can simulate any reasonable physical model with only a polynomial slowdown. This implies that efficiency is a universal property, regardless of the hardware. However, quantum mechanics challenges this, as classical machines cannot efficiently simulate quantum processes.
We must distinguish between two modes of operation. The deterministic machine takes a single step at a time, modeling how we actually find solutions. The non-deterministic machine, however, models a theoretical ability to guess the correct path instantly, or explore all paths at once. This concept allows us to define the class NP, which groups problems where a solution can be efficiently verified, even if the deterministic search for it is slow. How do we measure the efficiency of these abstract machines? We turn to asymptotic analysis, the mathematical apparatus for measuring behavior at the limits of infinity.
The most famous tool in our arsenal is Big O notation. It defines the asymptotic upper bound. In plain English, it guarantees that no matter how large the input grows, the algorithm's resource consumption will never exceed a specific growth rate, scaled by a constant factor. It is the ceiling of complexity, provided we have crossed the threshold, n sub 0. While Big O handles the upper bound, the Bachmann-Landau family gives us a complete vocabulary. Big Omega establishes the mathematical floor. It is crucial to note that omega defines a bound on the function itself, not necessarily the best-case scenario of an algorithm, although it is often used to prove intrinsic problem difficulty. Little o and little omega express strict inequality. For example, if a function is little o of n squared, it grows strictly slower than n squared, meaning the algorithm is faster in the limit. We can manipulate these complexities using cost function algebra. This system resembles a tropical semi-ring, allowing us to calculate efficiency without counting individual instruction steps. In this algebra, sequential steps follow the sum rule. Because the addition is idempotent, the larger term completely absorbs the smaller one. A linear step plus a quadratic step is simply quadratic. However, when we nest operations, like a loop inside a loop, we follow the product rule, multiplying their complexities. This leads to the dominant term principle. In a polynomial cost function, only the term with the highest exponent matters. Coefficients and lower-order terms vanish in the limit. This justifies why we can ignore hardware specifics. Fundamentally, n squared always grows faster than n, regardless of the constant multipliers.
Using this ruler, we map the landscape of difficulty. Computational complexity theory categorizes problems based on the resources required to solve them.
The three pillars of complexity are P, NP, and PSPACE. P represents problems that are practically solvable. NP represents problems where we can verify a solution quickly if given one. PSPACE allows for polynomial memory. Crucially, while this constraint is tight, it allows the machine to run for exponential time, vast but not infinite. The algorithm must still eventually halt. To classify a problem as NP-complete, a two-step proof is required. First, we must demonstrate membership, showing that the problem belongs to NP, because a solution can be verified in polynomial time. Second, we establish hardness via reduction. We take a known NP-complete problem, like 3-SAT, and prove it can be efficiently transformed into our target problem. Without the first step, the problem is merely NP-hard, not NP-complete. Finally, we must critique our model. Asymptotic analysis assumes inputs can grow to infinity. In reality, the universe is finite. A so-called efficient polynomial algorithm that runs an n to the power of 100 is useless in practice, often called a galactic algorithm.
Furthermore, Big O assumes a worst-case adversary, whereas real-world data is often far more benign.
Ultimately, computation is a physical process. Landauer's principle dictates that erasing information generates heat. An infinite Turing machine would eventually require more energy than exists in the universe. Thus, while our asymptotic hierarchy describes the limits of logic, it is distinct from the limits of the material world.